Hi, welcome to the solution to number 2 from the practice exam. So this problem asks you to imagine a slope with angle theta with two objects here. I'm just going to label them M1 and M2 rather than big M and little m. So there's M1 there, M2 there. They're connected by a string that runs over a pulley. And the string goes like that. So, what are the questions? Part A, we'll do them one at a time. So A says, if no friction, what angle makes them not move? Part B says, okay, now assume that the big one slides down the ramp. So B, C, D, and E is find the acceleration. So we'll do all that in one big bite. So B through E, if M1 is large enough to slide, find the acceleration. Okay, so let's get to work. As always, we draw force diagrams first after choosing a coordinate system. So I'm going to choose the conventional coordinate system that most of you will pick, which is that way is positive, and that for this object we have a tilted coordinate system like so. So now let's get to work drawing force diagrams. For M1, we've got three forces: gravity, a normal force. Let me just make sure that's in the frame. Yep, it is. Yeah, sorry about the messed up camera angles here. And then a tension, which I will draw in yellow to match the color of the rope I've drawn. And the gravitational force we need to break into components. So this angle here is the same as theta. So this component is going to be m1g cosine theta. That component is going to be m1g sine theta. Whoop. Well, but remember, it's that way and that way. And for M2, so it just experiences its gravity going down, m2g, and then the tension in the string going up. So part 1 says, if there is no friction, what angle makes them not move? I'm going to have three equations for this, although I don't really care about the y equation for number 1. So let's go ahead and write down all three of them. So I'm going to have x and y here, and then I'll write this as y2. So my x equation, let's see, I'm choosing up the ramp to be positive and down the ramp to be negative. So I will have t minus m1g sine theta, and it doesn't move. So this is equal to m1 a1x, which is 0. And then in the y direction, I have the normal force and m1g sine theta. Now, this is not really going to be interesting to me here. I will care about m1g cosine theta. I will care about this once I need friction, but now I don't. equals m1a1y equals 0. And then finally here, I have t minus m2g equals m2a2y, which is 0. Now, this equation here, I'm just going to cross out and write boring, because none of its variables appear anywhere else. But here, I can solve this, which just tells me that T is m2g. That makes sense. If this thing is just hanging here, then the tension in the rope must be equal to its weight. Substitute that in. So pull this down here. I get m2g minus m1g sine theta equals 0. The question was, what must the angle be? Ethan, I just saw your question. I'll grab that in just a second. The question here is, what must the angle be so it doesn't move? So I'm solving here for theta. I can divide through by ag. So if I am solving for theta, that tells me that m2 divided by m1 equals sine theta. So theta is the arc sine of m2 over m1. So that's the answer to part A. We have a question from Twitch chat. Ethan asks, in the previous problem, the one we just did, how did we go from 1 revolution per 3 seconds to 2 pi radians per 3 seconds? So the angular velocity, I gave it to you in units of revolutions per second. You had to convert that into radians per second. And there's 2 pi radians in 1 revolution. Maxiplier says, would I still want you to write up the y equation on the quiz, even though it's boring? No. You're smart enough to know what you need to solve a problem. I'm kind of going into gory detail on everything here just to kind of illustrate process, but you may, if you recognize that something is not important on the quiz, then you don't have to write it. So we did this. We figured out what angle makes them not move. Now, we're going to make m1 big enough that the whole thing slides. And now we need to find their acceleration. Now, the only thing that changes with the force diagrams once it begins sliding is that if m1 is massive enough to slide down the platform, that means that there's now a frictional force going up the platform. So now I'm going to write my equations again, but now put in this force of kinetic friction. So now, Maxiplier, now I will need the y direction. So let's see. I'm again going to have x for number 1, y for number 1, and then y for number 2 equations. So friction goes up the ramp, so it's going to be positive. So let's see, the frictional force is going to be mu k Fn. Our friend tension is still here, but pulling us back down the ramp is the x component of gravity as before. So minus m1g sine theta equals m1 a1x. Notice I'm keeping all my subscripts. I'll figure it out later, which a's are equal to which other a's. Not going to worry about it now. We'll worry about it later. Here, in the y direction, I've got the normal force and gravity again. I have Fn minus mg m1g cosine theta equals m1 a1y. And here again, I've got, come here, Chuck. I have again t minus m2g equals m2 a2y. So the same sort of algebra is going to happen, except now I need the normal force. Let me think about my accelerations and how they relate. I know a1y is 0 because I know that there's no acceleration perpendicular to the ramp. That's why we rotate our coordinate system. But these two are related. Let's see. If this goes up the ramp, that goes down. So I know, this is important, that a1x equals minus a2y. That's important. The biggest mistake people will make here is to just put one a variable for both of these without stopping to think that if this one moves in the positive direction, that one will move in the negative direction. So now that I know that, I can make progress. I'm going to solve the equation number 2 for t as before. This gives me that t equals, let's see, m2a2y plus m2g. But now I'm going to substitute. T is equal to minus m2a1x. I made this substitution here, plus m2g. All right, I used that to get my tension now in terms of the other acceleration. So now let me substitute this in. Well, I'm not going to substitute it in yet, actually, because I need to know how big friction is, and to do that I need to know the normal force. So I'm going to kind of come up here. This tells me that the normal force is equal to m1g cosine theta. So now I'm going to substitute for the normal force, this equation I just found, and I'm going to substitute for the tension. Let's see, what did I get? And t equals minus m2a1x plus m2g into the equation for x1. So let's just put these two things up there. So that gets me, so the friction term, I have mu k, and then I put in that. Whoops, I put in the normal force, so mu k times m1g cosine theta, so that's kinetic friction. Then I have the tension piece, so minus m2a1x plus m2g. I have the x component of gravity, this piece that's still there, so minus m1g sine theta equals m1a1x. Okay, so this is a big long equation, but we can figure out what all the pieces, where all the pieces come from. Blech. That's kinetic friction. It points up the ramp, so it's positive. This is tension. It points up the ramp, but keep in mind we have, there was a negative term in it. This is gravity. It points down the ramp, so this is all my forces, equals a1x. So the way to do the algebra, right, is I just take this term, I put it over there, and then I divide by a1x. So at the end of the day, what does this give me? it gives me A1x equals, I'm just going to kind of do the algebra all in one big bite, is mu k m1g cosine theta, that's friction, plus m2g minus m1g sine theta, all divided by, let's see, what's the coefficient of m1 of a1x going to be? This term right here goes to the other side, and then I divide by m2 plus m1. So while it looks gory, we can look at this and find pieces, all the pieces we'd expect the answer to have. Friction goes up the ramp. The weight of the hanging thing also pulls it over that way. The gravity, the x component of the gravity of this, so m1g sine theta, pulls it down the ramp. So these are all the kind of forces that act on the thing divided by the sum of the masses. So that's problem 2. Any questions about that from anybody who's watching now? I'm going to stop the recording here, and I'll see you for problem 3.